Thank you for coming to order in a reasonably short review time. I was remiss earlier in not introducing the affiliate faculty. These are people who work in industry or have worked in industry and are faculty mentors to the team. First person is Wayne Moore. Can you stand up? Wayne. Nicole Hamilton. Randy Tom. And lastly, Eric Swatam. Most of this is Eric's show. He's got 3 teams going. So our next, one thing about these presentations is kind of like the Ed Sullivan Show. It's just an olio of different things. So there's no consistent theme. It's whatever projects get done, present. So our next theme, the title is Facilitating Signal Production from Prosthetics Sensing Fingers. Professor Pierre Murat, who is a member of the faculty, the STEM faculty, the School of Engineering and Math, as well as a faculty member in the School of Medicine, and the faculty advisor, Eric Swatam, and I'll let the team introduce himself.
Thank you, Arnold. So I'd like to thank everyone for coming out tonight and for reviewing me and my teammate's national presentation. Our project name is, as mentioned, Facilitating Signal Production from a Prosthetic Finger. My name is Brian Pine. My teammates are Paul Hardwick, Joshua Wajaya, and Yara Kelly. As mentioned, we'd like to thank Dr. Pierre Murat for sponsoring our project. In addition, this effort was a collaboration. It wouldn't have been for the efforts of, once mentioned again, Dr. Pierre not only sponsoring our project, but being our industry advisor, as well as Ivan Owen, who is the 3D printing's chief technical officer in the 3D printing lab upstairs in Discovery Hall. As well as Dr. Eric Swatam for guiding us on this journey of a project for 2 quarters. In addition, we collaborated with a mechanical and electrical engineering team from Brazil. So a bit of background on what my team and I have been working for the past 2 quarters. We've been working on a prosthetic hand developed by Ivan Owen. Ivan Owen started creating this prosthetic hand by creating a costume hand, sending it online, and received a huge following. We received approximately 1.8 million views. A mother of a child from South Africa contacted him, hoping that he could work on the hand that her son never had. He was born without a hand. The child was approximately the age of 6. From that moment, Ivan said he took on the challenge head on. He then went into development. He then realized that the child was developing so quickly at his young age that garage materials were insufficient. 3D printing was the best course of action for his work. The picture shown right here is a development that is a prosthetic hand that he created himself from the help of him and a few other peers for the child. The key points of this project are that we were focusing on restoration of a lost sense and keeping it affordable for low income as well as developing countries. So what are we implementing? We're implementing haptic feedback. Well, what are haptics? There are the use of sensitive touch to a user interface designed to provide information to an end user. What does this mean? This means that we are taking the sense of touch, processing it digitally, and sending it back to the end user for as useful information. What is the technology used for? The main component of this technology is for a person with a prosthetic. They lose feelings in their hand. What they want to do is hold the cup, but they don't want to pull it too tight so it destroys the cup. They want to hold it just firmly enough without implementing too much force. So that way they can hold a paper cup, as I just did, as well for a newborn baby, or holding a hand of a lover without hurting them. What is the future of the technology? The future of this technology is very vast, actually. We can use anything from therapeutic massage to robotic surgery. So what is the solution that my team and I have come up with? We've come up with as a solution to create derives from information from a sensor, sending it to an amplifier and integrator, sending it to a microprocessor, and outputs it to the user using a vibrating motor. What this does, the key component to this the circuit was the amplifier and microcontroller. We had to create and program the microcontroller ourselves. So what it does is it reduces noise as well as sends a clean signal for the motor to send back to the user via frequency of vibrations. So what are the specifications that we're working with and what are the parameters we are working with in installation of this device? We're looking at approximately a size of 15.2 centimeters by 6.3 centimeters by 2 centimeters, which is roughly the size of a graphing calculator we're all fairly aware of. We get to keep the cost under $100, keep the weight under 200 grams, keep the delay under half a second, so when the person touches and uses the sensor, and when they receive the information under half a second, there must be an on and off switch to conserve battery life, and be able to output data from the computer via USB. The key component the key feature we were looking to implement into this circuit was the registration of tapping, whether they're using hard taps, soft taps, fast taps, or slow taps. Now I would like to hand it off to my colleague Cole for research and challenges.
Thank you. So we started our research off with the fingertip itself, which we were given a PVDF film sensor as our sensing device. The PVDF has several very useful features that makes it ideal for this project. For one, it has a very wide frequency range from 0.001 hertz up to 10 to the 9th hertz. It also has roughly 10 times the voltage output as piezo ceramic sensors. It has high mechanical strength and impact resistance, which is perfect for fingertips. It also is capable of resisting most moisture and chemical compounds, and it can be easily fabricated and secured to different types of textures. On the left, your left, you have the output of the sensor. These are several taps in sequence at different levels. As you can see, that signal is a very, very quick signal. It's very hard to get a hold of. This signal right here is a single tap when blown up. From this picture, you might not be able to see it, but it's roughly that first impulse is under 400 microseconds, making it very, very quick. So knowing that that signal was very quick, we decided we needed to, knowing that the signal only had a voltage output of about 200 millivolts at high hard taps, we know we had to amplify that signal. Another issue was also that the signal was very short. Because of that, we needed to stretch that signal out so the Arduino could get an accurate reading. In order to do that, we decided to stick with an operational amplifier integrator, which essentially lets us wave shape the input signal. On the graph here, you can see this dark blue line is our original signal, followed by the light blue line, which is our output from the amplifier. In our case, this was to increase the input signal active time. The final part was our motors. We needed a motor that was small or relatively small, as well as being able to have a large range of frequencies and amplitudes output. An LRA haptic motor provided these features to us. They're capable of being powered by AC and DC signals. They also have very short lag and rise times, making them perfect for quick responses and fast taps. They have a long lifespan, which makes it perfect for integrating into a hand that's probably going to be used every day. And they also have a very compact size. On the bottom here, you can see this is the breakout of the motor itself. This motor is just under the size of a dime, so it fits perfectly underneath the gauntlet of the hand that you can see out there in the front. This graph here shows the acceleration characteristics of our motor itself. It shows that it does have a range far enough that we can use. Once we finished our research, we began to test different designs. By testing those designs, we ran into several challenges that we eventually had to overcome. One of those was with filtering. Because we knew some of the frequencies we were getting were going to be noise, and we wanted to cancel them out, we decided to try to implement filters. Unfortunately, passive filters were dampening our signal to a point that we would need more amplification and thus more circuitry, which we could not fit on the hammer. Another issue was the low input active time, which I spoke about on the previous, or 2 slides ago. As I mentioned, the active time of the original signal was about 400 microseconds, making it very, very quick. For the Arduino that has an analog read of about 100 microseconds, meaning it can only get roughly 4 readings before the signal is gone. This is an issue because sometimes those readings would be 0, sometimes they'd be at the peak, but most of the times they didn't hit the peak of that signal. So we didn't actually get the full effect of that tap. The final challenge we overcame was negative input voltages to the Arduino. The Arduino does not like negative input voltages at all. So we decided we wanted to cancel those out. We originally decided to use a diode bridge, but that resulted in more issues. And ultimately, we had to scrap that idea. Next up, to go over how we overcame these challenges in our final design, is Josh.
Thank you, Paul. So, here is our final design of our amplifier circuit. First, the input, shown here, is first run off into the variable voltage multiplier, shown in red. Then, the signal generated by this phase is run through an integrator circuit, shown in green. Finally, the resulting signal is passed through a discharger, shown in orange. This phase is to ensure that the accumulated output didn't saturate the accumulated signal did not saturate the output. Finally, the voltage level of this charger is going to be put into the Arduino as the output of this amplifier circuit. We use an integrating amplifier to solve 2 of our most biggest problems. First is to increase the signal's active time. As Cole already explained previously, the direct input signal time is roughly 400 microseconds, and it's not adequate for the Arduino to read them reliably. Therefore, increasing the signal to active time is essential for the Arduino to reliably read the signal. Second is to eliminate alternating voltage level polarity. As Cole already said earlier, negative voltage reading on the Arduino will cause the Arduino to have a reading error. Therefore, keeping the polarity of the output in positive is essential for the Arduino to maintain an accurate reading. We also didn't add additional filtering because the integrator circuit itself works as a low-pass filter. Additional circuitry that we added is the variable voltage multiplier. Its uses is to calibrate the sensitivity of the device, therefore making this device could be applied to a wide variety of sensors. To test the circuit, to test the amplifier part of the circuit, we first run and make sure that 5 of these bullet points are fulfilled by our output. First, tapping the finger should excite the output voltage. This corresponds to an impulse tap. Secondly, harder tap should result in a higher voltage spike. This means that we can differentiate between a light tap and a hard tap and give an appropriate response to each. Sorry. When excited, the output voltage should have a long active time. As we already said earlier, the direct input has a very low active time, therefore could not be read reliably by the Arduino. Increasing the active time of the signal is one of our goals on our amplifier circuit. Fourth, no readable negative output voltage level. Sorry. As I already said earlier, negative voltage reading on the Arduino will cause the Arduino to have a reading error. Therefore, this condition is unfavorable for us. Finally, the output should discharge over a period of time. In addition of preventing an output saturation, as explained earlier with the discharger, this is also required that the output does not accumulate. For example, 3 small taps should not give a response of a 1 large tap. Here is the circuit test result of a single tap. We can see that a tap results in an excitement in voltage. And also, it also has a long active time. For example, this signal active time is roughly 1/10 of a second, more than 400 microseconds of the indirect input. Also, this doesn't have a readable negative voltage level. There is a slight negative voltage here, but it shouldn't be readable because it's so fast. Finally, the output discharges over time, which we can see on this picture. Next, I'm going to hand this to Yara, who's going to be in touch with the software part of the survey.
Our group chose to use an Arduino microcontroller for this project for several reasons. The first of which is that the Arduino is lightweight and it's very small, which allows us to meet 2 of our core requirements. The second is that the code is very versatile in signal processing. It allows us to take in both analog and digital signals and also output those same signals in whatever form we need to. It also has enough I/O ports to scale this project up so that it incorporates all 5 fingers of a hand instead of the original single finger that we tested it with. And the Arduino also has a built-in Adafruit library with more than 127 pre-programmed vibration methods. While we did not make use of that feature, future projects may make use of it. The Arduino code had 2 main functions, and that was to control the output to the serial monitor and to control the output to the vibrating motor. And this was done in 2 methods. The output to the LRA motor was done by taking in the amplitude from the integrated amplified signal and choosing what frequency had to be output to the motor to obtain the needed amplitude of vibration. The output to the serial monitor, very simply, is an output to the computer that is directly corresponding to the output that is taken in from the integrating amplifier. The Arduino was tested in 2 phases. Like the code, the testing had to be done with the output to the computer and the output to the vibrating motor. The output to the computer was tested by using a USB cord to connect the Arduino to the computer and to tap the finger several times. And we looked to make sure that the voltages that the computer was reading were accurate and corresponded with the voltages and the pressure of the taps that we were giving it. We did the same with the vibrating motor. We actually held the motor while we were tapping the finger and made sure that the strength of the vibration corresponded to the strength of the tapping. And in our final product, we managed to meet all of our specifications. The actual final circuit was split up into two parts. The first is the amplifying circuit, and the second is the Arduino, and this was simply done to fit around the gauntlet. The space that was there was not enough to fit the entire circuit in one area. However, the 2 sections are about the size of 2 different packs of gum, 6.5 by 2.5 by 0.2 centimeters and 5.5 by 4.5 by 0.2 centimeters. Our weight was 41.92 grams, which is about the weight of a pack of gum. We did also implement an on-off switch, which would conserve power when the product was not in use. And the total cost was $94.24. However, the majority of this cost was for the PCB boards, which were $40 each when we ordered 2 boards. However, the cost does decrease significantly when you order more boards. For 100 boards, the cost is a little less than $4 a board. We also, as I explained, managed to use a USB to transmit the data to a laptop and register different strengths of tapping and successfully outputted them to the vibrating motor. In conclusion, all of our specifications were successfully met, and we learned a lot from this project. We learned not to jump to conclusions prematurely, make sure we knew everything about our data and what we needed before we started working on a circuit and implementing phases. And along those lines is to make sure that all the parts we ordered are exactly what we want. The first time we ordered our vibrating motor, it was missing the wire leads and we couldn't solder any of them on because the pins were too small. We also need to pay attention to the Arduino limitations. Our signal was 400 microseconds long, and the Arduino takes 100 microseconds to read that signal, and at first we didn't realize that because, again, we had jumped to some conclusions. And lastly is the battery life. Our circuit takes approximately 112 milliamps, and our battery is 175 milliamp hours, which means that our circuit can only run for about an hour before it dies. This is easily fixed with a battery with larger milliamp hours. And we did find one with 880 milliamp hours, however the shipping time was such that we could not get it in time for this project. Power consumption can also be fixed. We can decrease the power consumption of this circuit, make it that we can use a smaller battery. And the motor sensitivity can also be improved in several ways. The first is just by getting a different type of motor. The second is by changing the Arduino code. And the third is by simply implementing a different type of sensor instead of a pressure sensor. And thank you all for being here. Does anyone have any questions?
I have one.
Yes.
You mentioned you needed to calibrate the device with the potentiometer. Was that to accommodate different users that might have different strength, or what was that for?
Josh, maybe you should answer this because that's your part.
Yes, it could accommodate for different users. Also, it could accommodate for different sensors, which could have a different sensitivity.
It was also partially a requirement from our advisor. We wanted to be able to vary it if there was that chance that a different sensor would be used.
Good question?
You guys are lazy.
I have one.
Yes.
Did you guys brainstorm at all on some sort of auto calibration procedure? I mean, I imagine that'd be pretty difficult, but
No, all calibrations must be on manual.
Well, another question.
Any more hands?
Okay. Thank you very much.